In this video, we're going to look at an application of the Poisson distribution to the number of arrivals of something over a period of time. So, for example, suppose that a company receives a telephone call and every hour they receive a certain number of telephone calls. And they want to know how frequently they can expect telephone calls. So suppose that lambda is the average number of phone calls they receive in an hour. Well, that would be the rate at which, so i.e. the rate at which the phone calls arrive. So this could be like 5 for 5 calls an hour on average, or lambda could be 0, right? On average, 0 phone calls in an hour. Although that would be if there were never any phone calls. Lambda, if the number of phone calls were very small, then lambda would be some small positive number. And we can use the Poisson distribution to approximate the probability that you'll get, say, 7 phone calls in an hour or 8 phone calls in an hour. And here is the idea. We've seen before that the Poisson distribution can be used to approximate the binomial distribution. So recall that the Poisson distribution, the Poisson lambda distribution, is approximately the binomial distribution NP, where lambda is equal to n times p if n is very large and p is very small, and if lambda is some moderate size number. How is that applied to this scenario? So take an hour, you take your 1 hour of time and divide it into a number of time intervals, say n time intervals. So n small time intervals, where n is, so n small time subintervals where n is really large. So n is some really large number. And it's so large that we can pretend that at most one call can arrive in a given time interval. This is where the fact that n is large comes from. So if n is really large and you assume that these phone calls are independent, then you can assume that no subinterval can have more than one phone call. So it's possible that 0 calls will happen or 1 call will happen per time interval. Well, that is where we can apply the binomial distribution, because the n time subintervals, for each of those, we get a trial where it's 1 if there's a phone call and 0 if there isn't a phone call. So the n time subintervals are Bernoulli trials where success means that a call has arrived. Well, given a time interval, if n is really large, then the probability that a phone call is happening in a given time interval is very small. So you have this scenario where you have a binomial distribution, right? The number of phone calls in this 1 hour it has a binomial distribution where n is really large and p is really small. And because of that, the number of phone calls in this hour can be modeled by a Poisson distribution. So the fact is, so the number of phone calls in this time period can be approximately modeled by a Poisson lambda distribution, where lambda is n times p. So the probability that there are k arrivals, or in this case, in this example, they would be phone calls, arrivals in the time period is approximately given by e to the minus lambda to the k over k factorial, where lambda is the arrival rate. Here's an example. Suppose that particles arrive on average twice a second. So 2 times a second. Find the probability of at most 3 particles in the next 5 seconds. So we can use the Poisson approximation. Particles arrive on average twice a second. So to say that the arrival rate is twice a second, that would mean that lambda is 2. But the problem is that we're trying to find the probability, so that would be 2 per second, but we want the probability of at most 3 particles in the next 5 seconds. So our time period is actually 5 seconds, and so our lambda should actually be 10. Because if particles arrive on average 2 times a second, then in 5 seconds, the average number of particles that arrive is 10, right? So this time period that we're talking about is a 5-second time interval, and so lambda is 10. 10 particles on average per 5 seconds. So find the probability of at most 3 particles. Well, at most 3, right? That means 0, 1, 2, or 3. So we need the probability of 0 particles in the next 3 seconds, plus the probability of 1, plus the probability of 2, plus the probability of 3. And by the Poisson approximation, right, so P of k is approximately e to the minus lambda to the k over k factorial, where lambda is 10. And so this sum that we have is approximately e to the minus lambda times lambda to the 0 power over 0 factorial plus e to the minus lambda. Let's just substitute. I don't know why I didn't substitute lambda equals 10 here. E to the minus 10 times 10 to the 0 power over 0 factorial plus e to the minus 10 times 10 to the first power over 1 factorial plus e to the minus 10 times 10 squared over 2 plus e to the minus 10 times 10 cubed over 3 factorial. Well, 2 factorial is 2. So this ends up being e to the minus 10 times 1 plus 10 plus 10 squared over 2 plus 10 cubed over 6. And whatever value that is, that's the approximate probability. So maybe instead of find the probability, the question should say estimate the probability. So that's an application of the Poisson distribution. So the main motivation for the Poisson distribution is that it can be used to approximate the number of successes in Bernoulli trials where n is large and p is really small. And sometimes we don't know what n and p are, right? And so we can't use the binomial distribution exactly. So, but if we know the average, then we can use the Poisson lambda distribution. And then we saw in this video that we can use the Poisson distribution to estimate the number of arrivals of, say, phone calls or number of arrivals of particles in a given time period.